Here we have a metric prefix table. You'll be provided with this prefix table on the test. It'll be projected on the screen. You certainly need to know all of these. You should always know these. These others you probably know from computers, Bega and Giga. And these two, nano and pico, are going to be in common usage in physics when we start talking about wavelengths of light. Wavelengths of light are usually measured in nanometers. On the next page, fundamental and derived units. There are only 4 fundamental units in the metric or SI system, which are very similar. But in the SI system, the 2 fundamental units that are on this list are mass, which is fundamental, and length, which is fundamental. All of the others are derived. Mass is measured in kilograms in the SI unit. In the metric system, it's just grams. But the SI system uses a more practical number because grams are rather small. The length in the SI system, as in the metric system, is the meter. Again, all the rest are derived from various other forms. Actually, I'm wrong. We've got one more on this list. Time. Time is a fundamental unit, and time in both metric and SI is the second. I thought there were only 2 on here, but there are 3 of the 4. The other one, which isn't here, is charge, and we'll talk about that in probably next semester. But these are the fundamental units that we're going to use now. The rest are all derived, so we could put a D in all of these other places. Area is just length times length. So the base unit for area is meters squared. Volume is just length times length times length, which means it is meters cubed. Density is mass divided by volume. We already know that volume is in meters cubed, so density is kilograms per meter cubed. And acceleration is the unit of distance divided by time squared. If we had velocity on here, it would be, let's see here, if we had velocity, that would also be derived, and it would be meters per second. Acceleration is meters per second per second. It's the change in velocity. So that's why seconds is squared right here. Some estimation. We all need to do some estimation in our homework, and we'll have to do some on the test. How long is your cell phone in centimeters? Your cell phone is a typical cell phone. It's 5 or 6 inches long. We could call that 15 centimeters. The next question says, is the mass of a raisin better measured in grams or kilograms? Well, a kilogram is about 2.2 pounds. A gram is actually really more like the mass of a raisin. The next question, how many meters is it from here to your car? Well, that depends on where you are when you're listening to this. But when we start looking at orders of magnitude, that's the easiest way. 1 meter would be near your neighbor, or the person sitting next to you, I should say. 10 meters would be in the next room. 100 meters would be a football field. That might be the distance to your car if you're sitting in class and your car is in the student parking lot. 1,000 meters would be, that's a kilometer, which is a little more than half a mile away. So If you're sitting at home, it might be 10 meters away, about just over 30 feet to the garage. If you're at school, it might be 100 meters away. How about the age of your grandma to the nearest power of 10 in months? Well, if we're looking at just powers of 10, she's obviously more than 1 month. 10 months isn't even a year. 100 months is approaching 10 years, but not quite. And 1,000 months is quite a bit longer than that. Certainly, that's going to be over 50 and under 100. So, if we're looking at powers of 10, this would be your best guess. The height of the ceiling in millimeters to the nearest power of 10. Remember that a millimeter, there are 1,000 of them in 1 meter. So if our ceiling is about 3 meters high, this is about 3,000 meters, or millimeters, pardon me. If we were looking at powers of 10, it would be somewhere between 1 and 10 meters. So it's somewhere between 1,000 and 10,000. 10,000 is way too much. 10,000 is over 30 feet. But 1,000 is only about 3 feet. Probably pick the most reasonable number. That would be short. This is more realistic. Let's look at some conversions. How many nanometers are there in 1 kilometer? So 1 kilometer is our given. 1 kilometer. I can convert this and say there are 1,000 meters in 1 kilometer. And that allows me to cancel kilometers, and I'm down to meters. The next thing I need to do is to convert meters into nanometers. So for every 1 meter, which I'll put on the bottom, I know that there are 1 times 10 to the 9 nanometers. So this number right here, I'm going to cheat a little bit. This is 10 to the 3, and this is 10 to the 9. When we're multiplying by powers of 10, we can just add these. We add these two numbers, and we end up with 1 times 10 to the 12th nanometers in 1 kilometer. That actually is kilometer. There we go. Convert 30 meters per second into kilometers per hour. So my given is 30 meters per second. Well, the first thing I'm going to do is I'm going to get rid of the meters. I'm going to say 1 kilometer is 1,000 meters. That allows me to cancel my meters. Now my units are in kilometers per second. But we don't want it in seconds. I know that there are 60 seconds in 1 minute. This allows me to get rid of my seconds, but now my units are in kilometers per minute. So the last thing I can do is say that there are 60 minutes in 1 hour. That allows me to get rid of these pesky minutes, and the units that are left are kilometers on the top and hours on the bottom, which means that my units will be kilometers per hour. That's what they ask us for, so this math must be correct. When I do this math, I end up with 108 kilometers per hour. If I was being strict, I might look at the number that they gave me that only has one significant figure, and I might just call this 100 kilometers per hour, since I can't round that up. to 200. But that's your answer. To this page, we're going to rank smallest to largest. So all of this involves understanding the prefixes for the metric system or the SI system. The smallest one that I can see on here is nano. So I'll call this 1. After nano comes micro, so this will be 2. After that is milli, which is 3. Deci will be 4. The reason I do this is 10 to the negative 9, this is 10 to the negative 6, 10 to the negative 3, and 10 to the negative 1. After that is 5, or is kilo, which is 1 times 10 to the 3. And giga, we've actually skipped mega. This is 1 times 10 to the 9. That's a billion. We skipped 1 times 10 to the 6, which would have been mega. The last page here, measuring the mass of a floor tile lab. I would have just said measuring the mass of a tile. What was the purpose of the lab? Well, that was to get the mass of one tile. And to teach you a little something. Why couldn't we just place the whole tile on a scale and measure its mass? It was too heavy for the scale. What is the same for each piece of tile? Well, that's an interesting question because there are a couple of things. They all revolve around one specific thing, and that's the thickness. All the pieces of tile had the same thickness. Well, if they have the same thickness, then if their mass per unit volume is the same, then they all have the same density. So, density, that is an N, density and thickness. I'll write that on here. That also means that they all have the same mass per unit of area. And that's what we were actually determining. Now here, the next question says, how do we use the ratio of mass to unit area of small pieces to find the mass of the whole floor tile? Well, we did that in two ways. One of them was by graphing the points and making a best fit line. Then we could take the area, let's say it was around 900 centimeters squared, and we could go up to our line, our best fit line, and go across and get the mass. Another way we could do it is to calculate the slope of this line, its rise over run, and create an equation. The next question says, what quantities did we plot? Well, we plotted the mass of each piece, and we plotted the area of each piece. This question says, why was the graph a straight line? Well, it was a straight line because we made it so. We understood that the change or the ratio of mass per unit area was probably linear because the piece was uniformly thick or had the same thickness throughout, and we presumed it had the same density throughout. That being the case, if we double the size of the tile, we double its mass. If we triple the size of the tile, we triple its mass, and so on. That means that the relationship is linear. Now, did our points come out to be linear? No. Some of our points were on a line, and some of them maybe not so much on a line. That's why we did a best fit line, and we made it straight because we knew it should be. Next question says, how do we use the graph to find the mass of the floor tile? Well, again, I've already mentioned that. We can go up from the area of a full tile and go across to get its mass, or we can calculate the slope of the line and do it mathematically. The last question says, what are some of the sources of error in our measurements? Well, there are several. The mass is probably not something that is going to be in too much error. Our centigram scales are both accurate and precise. We can measure down to the hundredth of a gram if we're patient with those scales. But the measurement of our area, that was subject to a lot of mistakes because the floor tile pieces, like the box I just drew around the word area, weren't necessarily square, meaning they didn't necessarily have right angles. Some of the edges were not straight, they were a little wibbly wobbly. We had to measure odd things like heights of triangles just by holding up a ruler to a piece of tile. So the area measurements were the measurements that were probably most in doubt. Now, once we had area measurements, though, we have another problem, and that is when we graph. If our points are not completely on a straight line, when we graph, we use our eyes rather than a computer to make a best fit line that is somewhere in between or around or through as many points as possible. That best fit line is subject to a little bit of interpretation too. I could draw a line through my highest point and through my lowest point, and you can see that by the time I get out as far as perhaps my floor tile, I could have quite different answers when I read across to the mass. This, or even something way up here. So our mass measurement could be anything in this area. We're hoping that it's going to be right about here because we hope we've got a really good best fit line. But since we're doing that by hand, that's a big source of error. If we wanted to, we could draw our line through our highest point and our lowest point. We could actually quantify, meaning give a numeric value to our error. And doing that by graphing is an acceptable way to do it. There are mathematical ways which you haven't learned yet, but graphical error analysis is quite acceptable.